We're jumping from chapter 6 to chapter 7 now. So we're in 7.4. Talking about arc length and surface area.
Okay, remember this.
Arc length and surface area often lead. Finding arc length and surface area often lead to interesting integrals. So what we want to do is we have some function. We have a graph of this function, and here's a small piece of our function. Let's draw a picture of our function. So here are our coordinate axes, x and y. And we're going to do a little derivation, come up with an expression for the arc length. So y and x. And we have some function, and this is a piece of the function here, graphed here. We're going to call this point down here. All right. Well, this is a small piece of our graph. So we're dividing we're dividing the graph into small pieces. So this is our x sub I. So we're going to divide it into little intervals. This is our x sub I, and we're at the f of x sub I is this point. And I'm going to call this point down here, we're going backwards here. So this is x I minus 1 and f of x I minus 1 at this point down here. And I'll call this point p sub I and this point p sub I minus 1. And my graph, my function is just y equals f of x, some function. So we're going to approximate the arc length by adding the lengths of the small segments over the curve. So I'm going to connect these 2 points with a straight line here, and we're approximating the length of the arc with the length of these small segments from p sub I minus 1 to p sub I. So. And the idea is, if we make the division small enough, this segment that connects our 2 points is closer and closer to the arc length of that segment over that little interval. Well, the length of this segment is d sub I. We'll call it d sub I for distance of the length of this little segment from p sub I minus 1 to p sub I. So d sub I is the hypotenuse of a right triangle made by my delta x sub I and delta y sub I. So d sub I is the square root of x sub I minus 1 squared plus the difference in the y values, f of x sub I minus f of x sub I minus 1 squared. So there's the length of this segment. I'm just going to say this is d sub I. The length of that segment is d sub I. And the sum, the arc length, we're going to approximate the arc length by summing these little segments. So the arc length, we'll say S, the arc length. And we usually use S for arc length. Arc length S is the sum. I'm going to say approximately sum I equals 1 to n, however many intervals we divide it into, of d sub I. So we're just summing those little segments to find our arc length. Now we're going to look at this interval from x sub I to x sub I minus 1. We're going to have to think back a little bit here. So we have a closed interval. We're assuming that our function is continuous and differentiable. It's a well-behaved function. Can we remember what the mean value theorem guarantees us on this interval? Yes. Right, yes, that's perfect. So Liam says there's a point, we have a point that exists in this interval such that the derivative at that point equals the slope of the segment between the endpoints. So the mean value theorem guarantees us that we have a point in this interval where the derivative of that point is equal to the slope of this segment. So that's what the mean value theorem guarantees us. So we're going to write that down. And I'm going to say MVT. So we have I'm going to call it W sub I. W sub I such that F prime at W sub I equals the slope of that segment. And the slope of that segment is just f of x sub I minus f of x sub I minus 1 over x sub I minus x sub I minus 1. So the mean value theorem guarantees us that we can find that point, or that point exists. And if I rewrite this, I'm just going to multiply both sides by the denominator here, or that f of x sub I minus f of x sub I minus 1 equals f prime of W sub I times our change in our x value. So let's rather than writing x sub I minus 1 and x sub I, I'm going to let x sub I, I'm going to say let delta x sub I, the change in the x value, equal this quantity. Just to simplify our writing. So using this quantity, I can rewrite my distance formula, my little piece of arc length, my d sub I. So d sub I equals the square root of delta x sub I squared plus f prime at W sub I times delta x sub I squared. And then I can factor out this delta x sub I squared, and since it's squared I can take it outside the square root. So I get that d sub I finally is the square root of 1 plus f prime of W sub I squared times delta x sub I. And our sum, our arc length, and our arc length we said was, make sure it looks like an S. S is the sum psi equals 1 to n as we subdivide these intervals, and we let delta x sub I approach 0. So we take the sum of these little segments of arc, and as delta x sub I approaches 0, we get closer and closer and closer to that arc length. So motivated by this derivation, what we do is we define the arc length motivated by this. So we went through this derivation as a motivation, and we're going to define our arc length. And the nice thing about definitions, I had one professor in college that said when you make it your definition, they can't touch you. Meaning that if your definition makes sense, you make it a definition. You don't necessarily have to. His point was you don't have to justify it. You've made this your definition. This is how I'm defining my arc length. Now we've gone through this derivation to come up with a convincing motivation for making our definition of the arc length what we do. So we're going to define our arc length. I'm going to switch pages here. Going to make this our definition. Define the arc length S of f on some interval to be S is the integral from a to b of the square root of 1 plus f prime of x squared dx. And we need f is smooth and continuous. And this quantity should be familiar. This is something that you guys have seen before for the arc length, how we find the arc length. But I just wanted to go through that derivation to show us our motivation for this definition. Questions on that? And I also like that derivation because we got to apply the mean value theorem, which is always nice. Mean value theorem always seemed like something that you learn and it's like, okay, yeah, that's nice. And then when you actually get to apply it to something else, I think it's fun. All right, are we good with our definition? Now, if you remember calculating arc lengths, often the integration can be these integrals because we have this radical, we have a 1 plus f prime squared, so we're taking the derivative of our function, we're squaring it, and we're adding 1 and we're taking the square root. Our integrals can often be very, very difficult. So a lot of times we end up using, to calculate arc lengths, we end up using our calculator to evaluate an integral numerically. But I wanted to show you a couple of applications where one, we know how to do something different with an arc length integral, and then when we do the surface area, I want to show you a little trick that's a good trick to remember in evaluating integrals that come up like this. So we good? All right. So our example. We have a cable hung between two towers. And they're 200 feet apart. And we mentioned when we talked about hyperbolic functions that cables, if we take into account their weight, the cables hang in a shape called a catenary, which is a hyperbolic trig function. So our cable takes a shape, the curve is called a catenary. And we derive the curve, the tractrix curve, the catenary curve is kind of similar. And it's a hyperbolic cosine function. So for this particular situation, we're given the curve. I'll write it both ways, exponential and in terms of our trig functions. And this is how could I rewrite this in terms of hyperbolic trig functions? You remember? Cosine. And I have a 75 and I have an x over 150, so this turns out to be 150 hyperbolic cosine of x over 1. So our cable hung between these towers takes a shape, and the 150 comes from the. If I draw this sketch really quickly, so here are our towers. If the cable hangs this way, these are 200 feet apart. If I put my 0 here, this is at minus 100, and this is a positive 100, x equals positive 100. The height here right in the middle is 150 feet. So the cable sags enough so that it sags by 50 feet in the middle. So that's where that 150 comes from. And the problem just gives us this, that this is the shape of our curve. We want to find the length of the cable between the towers. So that's what we're trying to calculate, is the length of our cable. And you could go through the problem using all the definition of this function with the exponential functions, but now we know how to work with hyperbolic functions. Let's go through this calculation using our hyperbolic cosine function. So y prime, what's y prime going to be that we're going to need to plug into our arc length formula? So we get sinh of x over 150, and y prime squared is just sinh squared over x over 150. So it turns out that we end up with a nice integral here. So our arc length S is going to be the integral, based on our drawing here, the integral of from minus 100 to 100 of the square root of 1 plus sinh squared of x over 150 dx. And what does that equal? 1 plus sinh squared?
That's cos squared.
Cos squared. And we're taking the square root. So we just get minus 100 to 100 of the hyperbolic cosine of x over 150 dx, which just gives us 150 hyperbolic sine of x over 150, and we're evaluating that on minus 100 to 100. And then when we evaluate this, we have to go back to our definition to evaluate this, unless you use your calculator. Yes.
I might have missed you saying this, but why is it negative 300 instead of like 0?
That's we could have done it from 0 to 100, and then our function would have taken a different form. Would it have taken a different form? Is that in the middle? I think it would be the same. I think we'd end up with the same thing. I think that's just how the problem. That just seemed that's how the problem was set up, and to me that seemed like a natural way is to set the center up at 0. And so we could. What's that? Yeah, x equals 0. This is so. If this is that's x, and y is going to go. Yeah, we'd have to shift the function. So rather than x over 150, we'd have to have x minus 100 over 150, I think. So we'd have to shift the function. Just the setup is a little different. So we can evaluate this. We could go back to our definition, or if our calculator will evaluate hyperbolic functions, we could evaluate it that way. And when we finally evaluate it, I'm not going to go through all the evaluation. We get that that it's approximately 215 feet. So I thought this was just a nice illustration that now we have an entire different family of functions that we can work with. Questions on that one? All right, I'm going to pause this really quickly, and I'm going to pass something out to you. So the results, so the handout that I gave you goes through the derivation. So the area of a surface of revolution. So we're taking a curve and we're revolving it about some axis, and we're finding the surface area of that thing that we formed. So our assumptions, we're saying that y equals some f of x for our first one, and it has continuous. The derivative is continuous on AB. So our function behaves nicely. The area S, and I'm going to use a capital S, is, our surface area is 2 pi, the integral from a to b, and I'm going to write r of x, and I'll explain that in just a second, 1 plus f prime x squared dx. And r of x is just the distance between the graph and the axis of revolution. So depending on how you're revolving the graph, depending on what the configuration is, r of x is just that radius of revolution. And we want to express, if we have y equals f of x, we want to express that radius as a function of x. So depending on how you revolve that curve, you want to express your radius as a function of x if you have y equals f of x. That's what r of x means. I just think of it as the radius of revolution as a function of x. If we have our graph as x equals g of y. So we have some function of y. It's the same thing. Our surface area of revolution is just 2 pi the integral from c to d of r of y square root of 1 plus g prime of y squared dy. And r of y is just the radius of revolution expressed as a function of y. So it depends on how you're revolving your graph around what axis, what r of y is going to be. You just want your radius expressed as a function of y. Question?
Can we pull the r out in front of the integral?
No, because r is a function of, here r is a function of x, and we're integrating with respect to x. So it's going to be part of the integrand. And down here r is a function of y, and we're integrating with respect to y, so that becomes part of the integrand. And I'm just going to say r of y is the radius of revolution. And a lot of times the books will give you 4 different formulas depending on whether you have a function of x, function of y, whether you're rotating about a vertical or horizontal axis. It's the same idea. I think this kind of condenses it, because you just have to think, I have a function of x, I need to express my radius as a function of x. When we're doing it this way, I have a function of y, I need to express my radius as a function of y. If you switch it around, say you had your revolving natural log of x, and you want to turn it around and make it a function of y, then you just have to keep that in mind when you're figuring out your radius. So your radius has to be a function of the function of the variable you're integrating with respect to. And again, because these have, the integrand takes this form, these integrals often are difficult. So I wanted to do a quick example to show you a trick, a little algebraic trick that comes up often in evaluating integrals that take this form. So a quick example, and then we are done. And I like, this trick is an easy, a lot of students kind of forget this one, and I like integrals that utilize the trick. So we're going to revolve y equals 2 square root of x about the x-axis, and we want this area of the surface of revolution between x equals 4 and 8. So just a quick sketch. Here's our little piece of surface of 2 square root x, and we're integrating from 4 to 8, and we're revolving this about the x-axis. So that's just a quick sketch of what we're doing, and we're revolving this. So r is, if I put this for this particular point, that's going to be r of x. So what's our radius of revolution here? How are we going to write our radius of revolution as a function of x? R is just our function. The distance from the axis to the function is just y. R of x is 2 square root x. So what we're going to do is revolve this around the x-axis. So we need y prime. Y prime is x to the minus 1/2 when I take the derivative of y. So we're going to be integrating our surface area. I want my s first. S is the integral from 4 to 8 of, and I've I'm going to put my 2 pi out here in front. Did I remember my 2 pi's back here? I did, okay. All right, so 2 pi, 2 square root x times the square root of 1 plus x to the minus 1/2 squared dx. So on first glance, to me, first glance here, this integral looks kind of ugly. But let's work with it a little bit. So I get 2 pi, the integral to 4 from 4 to 8. I'm going to write this as 4 pi square root of x, taking 2 out, square root of x times 1 plus 1 over x dx. So I just squared this and wrote it as a fraction. Still doesn't look great. Anybody see what we can do here? We could multiply them. That's one route. I think that's going to get messier before it gets neater. Anybody else have a suggestion what we would do here? So this is the form, this type of integral, this little trick when you have a radical that looks like this is a good one to remember. Lisa, separate in the separate integrals. There's something even easier that we can do. I'm going to find a common denominator here and add these two inside the radical. So this is 4 pi, integral from 4 to 8, square root of x, and inside my radical I get x plus 1 over x dx. Now does anyone see what we can do? We're almost home. How can I rewrite this radical? The square root of a fraction is, what's that?
There are a couple ways to look at it. You can multiply the x and just eliminate the bottom x.
Okay. I want to go the opposite direction. So rather than taking the x in, I'm going to rewrite this. You're on the right track, though.
Yeah,
Anna.
that's square root of x plus 1 over square root of x.
Right, there we go. Is that what were you going to ask a question, Anna? What were you going to say? Yeah, so we're going to rewrite it as the fraction of the square roots, and that's you were kind of looking at it both ways. Yeah, either direction. So I'm going to rewrite this as square root of x plus 1 over the square root of x dx, and then this looks much nicer now, doesn't it? These cancel, and I just get the square root of x plus 1 dx. And we know how to evaluate that. That one's an easy one to evaluate. U is x plus 1, du is just dx, so we just have the integral of u to the 1/2 dx. So, and we can evaluate that. So I'm not going to go through the evaluation. It's an easy evaluation. But I wanted you to see this little algebra involved here, because often when you have radicals and problems that you're given that involve arc length or surface area, the textbook likes to give you this kind of thing and make you go through that little manipulation to evaluate your integral. Yes.
In that second step, could you just restrict the x through something?
So you're saying take the x inside,
Yeah.
and so then it's x inside. Yeah.
Yeah, it's
Yeah. That would work. Yes. So I guess maybe I was hasty when I said that would get uglier before it got nice. Same idea. I was thinking the other direction. Same thing. Chris asked a similar thing. I was thinking get rid of the messy radical rather than, but yeah, it would be the same. All right, questions. So we've learned a couple of nice little tricks. This is a good one to remember. And our trick was multiplying through by e to the x when we have the e to the x plus e to the minus x to simplify those. So So those are two valuable tricks, nice little tricks to give them. All right, so page 483. And I want to look at something because I have these last three, for some reason I have them marked. So let me figure out why I have them marked.